This is the CDFAM podcast with recordings from the CDFAM Computational Design Symposium held in New York City, October 29th and 30th, 2025.
Thank you so much. My name is Jesus Marini Parissi. I'm the founder of Computational Design Engineer of Moon Rapid Adaptive Lab. And today we will be presenting what was the journey behind the PUMA Fast-R NITRO Elite. First, I would like to introduce MoonRabbit. We are a computational design agency dedicated to push the boundaries of performance products, and we go through innovation and design engineering. So we try to connect and have a team of multidisciplinary teams that can actually connect the parts of design engineering, because we know that there is a bridge missing in this area. Our work focuses on advanced computational workflows, so we try to enhance functions, efficiency, and innovation. So how did I arrive to this point? So my path to computational design started actually in the automotive sector because I have a background in mechatronics engineering. Then one of my passions was always product design. So I started moving forward into product design innovation, into design engineering, and finally I was able to be part of the MIT Design Lab, where I had the opportunity to do research and development in product design. So today, I'm bringing a question. What car crash and running or footwear have in common? I will say that not that much, but we try to bring that gap together. So for us, part of these workflows was the idea of bringing what we know with PUMA in order to create like what will be the future of running. So this was the PUMA team, in the PUMA innovation team, that took the challenge to us, or we took this challenge all together. So we were able to put a lot of back and forth in order to understand how can we use new techniques and new technologies in order to create better and faster products. So we came up with the idea of what if we use it for the race day shoe. So 2020, they start this PUMA race day shoe line. That actually, it was really interesting because it has a decoupled midsole, so two pieces, a carbon plate in the middle. So it was the perfect challenge for engineering, because you have pieces of foam, pieces of carbon, and you have different stiffness through, you have a rubber piece. So it was really, really interesting to approach this challenge. So the brief was basically, how can we create the next generation of marathon running? I don't know how many of you have worked in the footwear industry or in any industries. Every time they start from the 2D. So this was quite different from me, with coming from an engineering background. Actually, starting from a 2D was weird. So we wanted to start with a 3D approach immediately, to start seeing mock-ups, digital mock-ups, creating prototypes, creating forms, seeing shapes, design, and so on. So we proposed a way in which we could translate the previous model into a 3D design space and create characteristics to understand the structure and performance. Besides that, we wanted to put the part that we, let's say, masters, because that's 6 years I've been working in only simulations for hyperelastic materials or soft foams or rubbers. So how can we create a multi-material simulation that enables the understanding of footwear in general? So we can observe the physical behavior, we can have like an X-ray or like a macro vision of what's happening in actually maybe 250 milliseconds. So we propose a workflow. This is also really interesting, because for us it's always about the workflow and how these kind of workflows not only can apply for footwear, but it also can extend to different industries. So how we did this? We started by collecting data. So PUMA has a NITRO lab in Boston. So they have a really cool setup in which you can get plantar distributions, treadmill videos, ground axis forces. So how can we put all this information together? So at the end, it's data that is trying to talk with the product. So one way to do it is by experience. The other way is trying to put all data in a design space. So something that we start collecting is creating a huge database. So we start inviting runners, we start putting more information in order to create enough statistically available data that could actually help us to lead the design. One of the main characteristics that I believe is important when we are doing projects in design engineering is about material characterizations. So you need to know actually what you are working with. If it's a hyperelastic, a plastoelastic, or a carbon fiber, what is the considerations inside? So you need to understand the tension, the compression, the biaxial behavior, and so on. This was really critical for us to put a correct simulation setup. And then we needed something or somewhere where to put all this information in a 3D design space. So we got our inputs, then we created our computational data processing. So this is the space or the black box or our area in which we will start transforming data into 3D. And how can we visualize it? How can we actually work with that? So this was the challenge for us, but at the end we start creating our own tools, because custom tools in this case was one of the key elements for creating what will be our performance area, because we start creating clusters in Grasshopper with different definitions. We create our own API for FEA. We start creating different definitions and workflows for data visualizations, and then this helps us to loop faster and faster between one area and the other. So, simulating multi-material physics was not as easy task. So at the beginning it was really complicated to get it right. So you need to understand what are the correct balances of forces, what are correct the timings, the materials, and so on. But finally we got it correct. And this is part of the success of this project, because we were able to validate the models, the digital models, with physical testing. So we knew the deformations, we knew the strengths, we knew the forces, and this helped us to move forward and believing what we were doing was correct. So we start mapping, like digital simulation enables the creation of different geometrical changes at the same time that you can variate materials. So you can test different type of foam, different types of rubber, you can have different type of, let's say, internal plates, could be PAs, carbon, etc., and have everything digitally tested. So we proceed to do that. We created a material testing with the same model of the Fast-R 2, and we start learning from it. We start learning which materials were having the best response, the best timings, the best energy absorption, the correct bendings. And once that we understood all of that, we kind of put all together in a way that we can actually use the information. So we start creating heat maps, we start creating volumes, and we start creating our own KPIs in order to understand how can we use this information to create an informed decision in design. The next step for us, I think, was the digital mockup. Digital mockup was really important for us, because having the possibilities to create fast prototypes in terms of days, maybe weeks, test it, and go back and forth once again. So that was the key element that we start implementing. So once that we have the information from the Fast-R 2, and then we start guiding the design of our digital mockups, we were able to also simulate those digital platforms. So we couldn't understand if our designs were making sense or not, and where were the areas of opportunity in order to improve a compression, improve a stress, or to guide better the directions of forces. Along with this, it was always important to have the DNA or the design part inside the project. So this was a key feature in which you start creating the mockups, but then you start aligning the design. So everything comes together, the engineering part, the design part, and the production side. So little by little we came up with the first sample design, and then we started iterating between different materials specs. Here we were to the microscope. Literally, we start creating different specs, different forms, the changes were minimal, but we knew that we want the maximum performance. So how can we achieve actually the best of the performance in each piece? What was the correct material in order to enhance the performance of the carbon plate, in order to guide the energies in the correct directions? What were the foams? What were the rubbers that, and the patterns inside the rubber that enabled the best traction? So all of this was possible to be tested through simulations and digital testing. One important thing for us was always the weight, but also at the same time keeping the DNA of the brand. So that's why we always keep in mind how is the construction of the shoe, what's the storytelling that is coming through, and how can we actually create a shape or a design that actually follows this. So this was the first sample of the Fast-R 3, or the Fast-R development, in which we could reduce the development time by 30%. We cut a lot of material waste by molding making and fabrications, because we did everything digitally tested. At the end, of course, we have to have physical samples. We need to go back, test those physical samples, understand if they make sense or not. But this helps us to create more informed decisions when we're creating design. This is the ones that we got the first prototype. Then the next part was testing and testing and testing, saying wearability, performance, if it was making sense of what we were doing digitally actually in the physical world. And then we saw that it was correct, and then we were in a good direction. We have maybe around 95% of correlation between what we did digitally and what was physically. And then from there we start doing design, detailed design modifications. With the design modifications, we finalize with always with a simulation to understand that all the designs and details, they don't change the performance of our shoe. Probably in the full project we spent around 300 hours of simulations. We did more than 100 material combinations between them, and we got the carbon and foam optimized to have the most advanced running experience. Something that is a highlight for us was the importance of the carbon plate design. In the carbon plate design, we try to understand and analyze each of the layerings inside those carbon plates, and using all the data set and all the data that we got from the athletes in order to get the best configuration possible of the layerings. So this is also one of the big achievements that we were able to use, because in that way we could actually test what directions, what angles, what layering, in which moment we need to do it. And finally, thanks to the machine of PUMA, they were able to put everything ongoing. So they start creating all the color material finishings, they start trying to test it with different influencers and bringing people to the lab, testing the part of the finalized project. And then finally we got it right. And it was presented thanks to the project 3. Fast-R 3 was launched in the Boston Marathon. And it was a huge thing for the footwear industry, because it was one of the first, I mean, for PUMA and for us, was a reduction in 95 grams from the previous tooling, but having the same performance. We increased the 25% energy returns. Also, this is thanks to the new NITRO foam that is a TPU based. And the minimalistic upper, we will have a sample of the shoe there, so you can also see how light it is. The performance impact of the Fast-R 3 is that it got sold in 3 days, 237 pairs. At the Boston Marathon, thanks to the Project 3, 30 of the 90 marathons that were part of this project break their personal record, and 4 athletes were present in the first 20 par. Amal Petros, this is one of the craziest highlights. Amal Petros was a silver medal in the men's marathon in the World Championship with a photo finishing. This is something that never happened before. By 0.003 seconds, he got the silver medal. So it was a good achievement for us to see that actually the shoe is helping athletes to move forward and to perform better. Another highlight is, I don't know if some of you run and know how difficult it is like go below 3 hours marathon running. So cutting 4 minutes in your pace and your race is something really important. And finally, this shoe got a lot of compliments during this year and also got into the Times best inventions. So we are really happy to be part of this project. Something that this is a video that I would like to show you, like in a nutshell. This is how it looks one day in our studio. Hope you like it. So this is we are a team of 5 persons in the studio, so we are really small, but we are doing great things in trying to push the future of computational design. So the takeaways is we explored the 3D design space, identifying areas of opportunity. We created all our custom tools and trying to adapt different platforms between one and the other. We try to optimize the structure for performance and efficiency. We reduce the production time and physical prototyping, which is also important, and we help to PUMA to create faster and better informed decisions. And finally, the workflow is not limited to footwear. We try to scale this one in different areas and try to find different opportunities in, I don't know, consumer electronics and other consumer goods areas, automotive, industrial, audio systems, etc. Because at the end, data is in everything. So if we have good data, it's possible to create a specific workflow to improve and create better products. Thank you.
To see the full recording of this and previous presentations, as well as information about future CDFAM events, visit cdfam.com.